Hey everyone, thanks for taking time out of your busy schedule to join us for today's webinar. I am Dr. Joe Schoonover over here at Fluid Numerics. I'm an owner of the company. We started back in 2017. I'm also spending a lot of time being a research software engineer. Before we get started, just a few housekeeping items I want to just go over. Feel free to use the chat to introduce yourself, ask questions, and engage with the content. The chat window you can find on the right side of your screen. At the end of the webinar, we will have a Q&A session. You can submit any questions you have for me anonymously through the question portal, which you can access by toggling over to the questions tab below the presentation window. You can post your questions through the chat, and we'll do our best to comb through those at the end of the webinar and address those questions you might have. Finally, this webinar will be available on demand after the conclusion of today's event. You'll all receive a link to the recording, so feel free to share that with your colleagues, anyone else you think might be interested in any of the content we're talking about today. So yeah, today we're going to be talking about PyTorch performance on AMD Radeon and Instinct GPUs. I'd like to just throw out a special thanks to my co-author on these slides, Garrett Bird, who's also at Fluid Numerics, and then some of our collaborators at Florida State, at SUNY, and at CNRS in France. So this talk today is actually not a talk about artificial intelligence, machine learning, or any of those topics. However, if you use PyTorch or are planning on using PyTorch, you'll probably find some of this stuff interesting. We will be talking about some of the system administration side, like basic installation and setup, some potential hurdles you might encounter when doing that. Just based on what we see discussions, how those evolve on the internet and various forums. And of course, we will be talking about some benchmarks we're running for some general purpose applications we've built that use PyTorch for the GPU acceleration. Now, on our end, the problem of interest today that's really going to be the focus of a lot of the benchmarks is that we are actually interested in calculating kinetic energy spectra for fluids in irregular geometry. So if you're not in a CFD background, this might blow right by you, but the point of kind of introducing these concepts here is so you have some understanding of the computational complexity behind some of the benchmarks we're going to be presenting later on. So the motivating problem that we look at in the oceans and the atmosphere, there is a variety of circulation patterns that are out there. And one way that researchers who develop numerical models use to assess sort of the validity of the code is to look at kinetic energy spectra. What we're looking at here in this video is what we call the vorticity. It tells us at each grid cell how much circulation there is in the flow. And if I play this again, you'll see there's like various size red blobs and blue blobs. And all of this is in some sense related to the amount of energy at varying length scales in the fluid flow. Now, of course, in reality, what folks often do is they use something like a Fourier transform to calculate kinetic energy spectra, which has its own drawbacks, particularly if you're in the oceans where you do not have periodic boundary conditions. You have coastlines and irregular boundaries. Fourier series actually don't do quite well at capturing the energy spectra. So we're looking at a method to capture that spectra that does not suffer from some of the assumptions that Fourier series require, particularly when you're using Fourier series, data needs to be doubly periodic. You need to have nice square domains. And all this comes down to doing a heck of a lot of compute, which AMD GPUs are well suited for. So let's go back to our days of calculus and talk a little bit about our motivating problem so you can understand where we're coming from in these benchmarks. What I've got shown here is just an arbitrary domain. It's got some weird wonky boundary. The domain is labeled as A. The boundary is partial A, and it's got a outward pointing normal and a tangent vector. So we have some way of numerically describing what that domain looks like. And we have a vector field, U vector, just a 2D vector field. And what we do is we appeal to what's called a Helmholtz decomposition. Effectively, what we're doing is splitting the flow into a rotational part and a divergent part. That's just basic calculus 3. The nice thing about doing this split is we can separate the velocity field into an equation just for these two potential functions, psi, which is related only to the vorticity or the amount of rotation that the fluid might have, and we relate the other potential to its divergence. From here, what we want to do is, because those were elliptic equations that we can work with, we can write the solution to those elliptic problems as a sum of eigenmodes of the elliptic operators. And all this to say is this is exactly what Fourier series does, except that Fourier series assumes that the boundary conditions are doubly periodic. And we've generalized this so that we can use homogeneous Dirichlet boundary conditions. So we set the solution to 0 on the boundaries, and we have homogeneous Neumann boundary conditions for the other set of modes. We can then write those potentials as some linear combination of those eigenfunctions. So the idea being, once we have those projection coefficients, we can actually calculate the amount of energy associated with specific length scales. The length scales we can derive from what those eigenvalues are. All right. I know I've said a lot of stuff related to calculus and partial differential equations and linear algebra. The key takeaway here is that the problem we're after is actually calculating these eigenfunctions. So we need a way to one, discretize that Laplacian operator, so this becomes a matrix system, and we have a matrix eigenvalue problem to back out. So once I have my geometry defined, I have my discrete Laplacian operator. Essentially, I'm doing eigenvalue search, which, of course, built into PyTorch, there are functions like that, like eig or eigh, but I'm going to try to convince you that there are reasons why we don't want to use those for the problems that we're working with. So remember, in general, what we're after today in our benchmark problems is finding eigenmodes of these Laplacian operators. And what we're actually going to do is implement a matrix-free eigenpair solver using a slightly different method than what's available in eig or eigh. So there's a few reasons why we don't want to use eig and eigh directly. For one, coming into this problem, we have functions or subroutines that implement the action of a Laplacian or a Laplacian inverse. So in other words, you give me a gridded set of data, and I can return back from this function the action of the Laplacian on that data, or I can tell you what its inverse is. Now, the torch methods like eig and eigh do require that we would actually construct a matrix representation of the operator. In the case of a Laplacian, if you're doing things like finite difference, finite volume methods, that's actually not too bad because those matrices are sparse. You can store the main diagonal and the off diagonal components and just use a sparse matrix representation. So that might be okay, but there are some other reasons why we still don't want to use this approach of using the built-in methods. One, we don't want to waste a lot of time reshaping arrays. Our data comes in usually as 2 or 3D gridded data. Torch methods and even like SciPy methods out there that do eigenvalue search problems, they actually require you to store the data as column vectors. So you have to spend some time reshaping arrays between your native data storage format and a column vector and kind of getting that right. We don't want to waste time just kind of doing that kind of remapping. Last, and this is probably the most important one, probably should have started with this reason, but for our problem sizes, returning all of the eigenvectors is actually quite impractical due to the memory requirements for doing that. And eig and eigh, those methods are meant to return all the eigenvalues and eigenvectors of a given matrix. Now, this problem I'm presenting here is actually a fairly small problem. So for a grid with 500 by 500 points in it, if I just use single precision, we would need about 250 gigs of memory just to store the eigenvectors. This comes from the fact that if I have 500 squared points, there's 500 squared eigenvalues and 500 squared eigenvectors. You can tally all that up, multiply by 4, and get the amount of space needed for storing that. Now, the actual memory footprint for doing the eigenvalue decomposition, which involves QR decomposition, would take basically another factor of 3 to 4 on top of that, so close to about a terabyte of memory just to do the decomposition problem. So it's not quite practical for our use case. In addition, we're always not necessarily interested in having all possible modes. We're actually quite comfortable for our applications looking at a subset of eigenmodes so that we can calculate spectra in sort of length scales that actually matter to us. We don't need to actually have all of them. So we can work with something a little bit more efficient. Now, if you've done work in this area, you may be familiar with this, but I'll try my best here just to give you a high-level overview of sort of how this method works for calculating only a subset of eigenvectors and eigenvalues. Because again, when we get to our benchmarks, you'll have a little bit better understanding of what it is we're actually running. So what we're looking at is what we tried to implement in PyTorch. What we did implement in PyTorch was a matrix-free implementation of the implicitly restarted Lanczos method. What this method does is it develops a different representation of a matrix here. A here would represent our discretization of the Laplacian or the Laplacian inverse. We construct a basis of column vectors to project on that are stored in this matrix V, and that gives us out on the other side that you can write this equivalence to that same V matrix whose column vectors you're projecting onto, and a matrix H. Now the key thing here is that if I have an n by n matrix, so if I have my 500 by 500 grid, A would technically be a 500 squared by 500 squared matrix. M, this little m here, we can actually choose a much smaller number here for M, so we can establish somewhat of an equivalence between A and this matrix H. There's some unique properties about this relationship that, for example, one being the eigenvalues of H are shared with the eigenvalues of A. And if I find the eigenvectors of H, I can map those to eigenvectors of A. Now, the key point behind the implicitly restarted method, it is an iterative method, and I've added this little remainder term here that we keep track of when we do this decomposition, because we don't do it complete every time. So the way this would work is I pass in a single column vector into our method, and it generates m additional vectors on top of that, and it will keep iterating this process, re-choosing that initial vector so that we can drive down that residual so that we get exact equivalence AV equals VH. Now, once we have that, we can absolutely run torch.eig, or in this case, torch.eig, since this is a symmetric matrix, to spit out the eigenvalues and eigenvectors of H, and then use the relationship we have here to then calculate the eigenvectors of A. Now, the way this decomposition is actually done, if you're familiar with orthogonalization, essentially that's all we're doing is we're taking in that initial seed vector. We're going to do the matrix applied to that vector, and then remove all the components that are parallel to all the previous vectors we've generated. So we're just creating an orthonormal matrix V here, and then storing those projection coefficients in H. So that's basically how that works. So there's some tricks you can employ here for our case, when we're trying to calculate spectra. We know that if A corresponds to the discretization of a Laplacian operator, the largest eigenmodes of A, which is what this will return, is going to give us the smallest length scales of A. If instead we use the Laplacian inverse, for example, if I have a subroutine that implements like a DST, or if it implements a conjugate gradient method to invert a Laplacian, what I can actually return the eigenvalues and eigenvectors associated with the largest length scales of A. The other trick we can do is we can sort of bandpass things and say do a shift and invert. So if I pass in instead A minus sigma times the identity matrix and then invert that, what I can do is actually tease out the modes that are closest in magnitude to the eigenvalue sigma. So this is all quite useful for constructing subsets of the eigenvector space. I'm more than happy to talk about this kind of stuff, but I'm sure you guys are here more for the PyTorch side. So here's kind of what the implementation looks like, which you can find on our GitHub. So that's github.com/fluidnumerics. The code is called FluidSpectraEig. There is a module in there called MF EigenTorch that implements both an implicitly restarted Lanczos method for symmetric matrices, as well as an implicitly restarted Arnoldi method for non-symmetric matrices. But essentially what it does is it takes in as the first argument a procedure called matrix action. This actually points to a procedure that would take in a set of data, X, whatever shape you want that to be, and spits out another set of data with the same shape. Now, the assumption is that that matrix action is, when you're using the Lanczos method, is that the matrix action is going to correspond to something that would have the equivalent of symmetric positive definite form if you were to write it down as a matrix. And in this way, it kind of steps away from this idea that's behind some of the APIs for like SciPy or even the built-in Eigen EigH, is we do not need to actually construct a matrix. You just need to give me a routine that implements the matrix action, and then we can go from there to calculate the m or m plus k largest eigenvalues and eigenvectors. The way this is called, so this is the sample subroutine that we're actually going to be benchmarking today, we would, down here on this line here, we have evals, eigenvectors, and R, which is the residual of that iteration process. We call the implicitly restarted Lanczos method. The first thing we send in is that matrix that goes in, the matrix action that goes in here. So this first argument here, the self Laplacian G inverse, this is actually implementing a inverse of a Laplacian that's actually pulled from another piece of code called MQ geometry. MQ geometry was actually what was used to generate the simulation you saw on the first slide. It does what's called quasi-geostrophic equations, which is primarily what was used for a long time to do weather forecasting and oceanographic simulation back in the 90s and even into the early 2000s. MQ geometry is unique in that it was also written using PyTorch, so that we can actually do our full matrix inversion also on the GPU. So everything is fully resonant on the GPU when we do this run. Now the inverse itself is it's actually using a discrete sine transform method to do the inversion process, and to handle irregular geometries, it's using a capacitance method. In case you're familiar with those kinds of solution techniques. So yeah, that's basically it. We call the method just like this, passing in the matrix action that we want to use. Here we're going to be using the inverse. So we actually do quite a bit of work for each iteration to spit out each of those basis vectors that come out to fill out those columns of V. We send in an initial seed vector that satisfies the Dirichlet boundary conditions so that we don't have sort of garbage seeding this whole process off. And then it's just going to return back to the main program eigenvalues, eigenvectors, and the residual. Now, the simple problem we'll be benchmarking is actually a square domain where you can actually write down the exact eigenvalues and eigenvectors. This was done simply so we can verify that we're getting the correct answer, because it wouldn't mean anything to me if I got fast code that gave me a bad answer. That would just be absolute nonsense. So we did want to pick something where we could actually verify that we're computing the right thing. So if I look at a number that tells me it's running so fast or so slow, I actually know I'm at least on the other side of this getting out the correct answer. So what we're going to do is look at the Laplacian on a square domain. Again, Dirichlet boundary conditions. We're going to calculate little m eigenpairs. So that'll be a variable that we tweak in our benchmarks. On an capital M by capital M grid, this is also a variable that we will be tweaking in our benchmarks. And these are really going to be what's going to control the problem size for what we're doing. And the other little hint, the other little trick here with this method is if you want to find m eigenpairs, you need to actually have a search space that's slightly larger than m. So we're going to have what's called a Krylov search space of m plus k. K is typically only like 10 or 15. So for example, if I'm looking for 100 eigenpairs, I would probably have 110 or 115 vectors in that search space. Down at the bottom, I'm showing two plots. On the left, on the bottom, I'm showing just an example of some of the results from a very coarse resolution setup that we had, just part of the verification process in case you're interested. On the x-axis is the exact calculated eigenvalues. And on the y-axis is the ones that we numerically calculate. If we get everything exactly right, all of our blue dots here would lie on the green line. But you can see as we get out to some of those higher modes, we do see some, a little bit of disagreement with the exact system, but this is actually not too bad for our purposes. Really what this affects is our ability to associate a specific amount of energy with a particular length scale. And as long as we have some understanding of how big those errors can be, and they're not too large, we're actually quite happy with this. And on the right side, I'm just showing a few of those eigenfunctions that come out of this process. So here's just the first 6, which are corresponding to the largest length scales for a square domain. Surprise, surprise, they're just cosine modes, so nothing crazy. They're just sine modes, so nothing crazy going on here. All right, so if you are not comfortable with calculus, or you're like, what the heck is going on? Your brain might be doing this at the moment. So let's take a moment, hit Control, Delete, and we're going to shift gears and talk a little bit about how to set up ROCm 6 and PyTorch. No matter what you do, I highly recommend, before you get started, especially if you're setting up a system for the first time, definitely check the ROCm documentation. AMD has done a terrific job in the last year about stepping up their game with documentation and really starting to support a broader range of their GPUs and really documenting what things that they're actually testing and what things they're not testing. So every time you hear me say the words supported, or AMD supports this operating system or this GPU, what it means is that AMD is actually testing for those operating systems, for those GPUs. They're shipping pre-compiled packages for that operating system's package manager. That's all that means. Now, this is to say that this list that I'm showing here, which again you can find at rocm.docs.amd.com, this list is not fully exhaustive on where you can actually find ROCm in the wild. This is just what AMD supports. There are other operating systems like Debian and Fedora that have their own builds, and those teams are actively supporting those for those operating systems. However, like I said, if this is your first time, I highly recommend just sticking to this particular list to get going. Otherwise, you'll be having to consult the other operating systems documentation to get that ball rolling there. 2 things to look at. One is, of course, the operating system flavor. So whether it's Red Hat Linux, whether it's CentOS, whether it's SUSE or Ubuntu, you also want to know what version you're working with, and specifically the kernel version that comes with that. Particularly what I found with Ubuntu, which we'll be talking about those today, the Ubuntu 22 and Ubuntu 20, is that the Linux kernels that are shipped with those out of the box are not necessarily compatible with the latest version of ROCm. Instead, what you need to be doing is, after you set up Ubuntu, you will probably want to enable or install the hardware enablement Linux kernel, which we'll cover here in the next couple slides. If you're new to the system administration game, there's two things you can run on the command line to spit out what operating system you're on and what Linux kernel you're on. So if you just cat etc release, look at the version line, that will tell you the exact version for that release of, in this case, Ubuntu. And if you run uname -r, you can spit out that kernel there. So in this particular case, you can see we're running Ubuntu 22.04.3 with the 6.5 Linux kernel. So again, you just want to make sure you're matching everything before you start trying to install things. Otherwise, you might not have such a great time. There are 2 different installation methods for AMD GPU drivers and ROCm. So you can use the AMD GPU installer. It's really just a deb file that you can download from AMD directly, and it provides a wrapper around the system package manager. By using that tool, it will handle a lot of things that, although yes, you can do it by hand, it does make the process quite easy. So you can add repositories to the system package manager. This includes things for both the AMD GPU drivers as well as the ROCm packages. It will take care of handling the AMD GPU driver install as well as other ROCm components based off of use cases that are probably more understandable. So that way you don't need to necessarily know all the specific packages within ROCm that you want to install. This is definitely ideal if you're not as familiar with working with the system package manager. I've actually found it to be quite nice, even though I do this kind of stuff a lot. I've actually found it quite nice for managing multiple versions of ROCm installations. So if I want to use a fixed version of the AMD GPU drivers, but have multiple flavors of ROCm available for testing, This is actually a really nice way to go for managing your ROCm installations. Of course, the other route, because all the AMD GPU installer is doing is underneath the hood using the system package manager, you can do that yourself as well. In that case, what you'll need to do is, of course, you'll need to add the repositories manually to your operating system's package manager. You can take care of installing whichever AMD GPU drivers you want, and then adding ROCm components on top of that. So if you're comfortable with that kind of workflow and you're more comfortable just using the package manager on your operating system, this is a great way to go. Like I said, AMD GPU installer is there if you just want to make your life a little bit easier. So here's an example of doing the AMD GPU install setup here. So there's just 3 lines really to get going. First one, this is just an example for Ubuntu 2204. You wget the deb file for the AMD GPU install script. Go ahead and install it. That gives you the AMD GPU install binary that you can use to do all that work for you. In this case, if we just use AMD GPU install use case graphics, ROCm, that will take care of doing the driver installation and the entirety of ROCm. So that includes HIP, the MIOpen, all the additional libraries that you would want. For other operating systems, because I'm not going to spend the whole time just kind of going through every single possible incantation out there, definitely check out those ROCm documentations. They have a great tutorial to help you quickly get started, again, both with the AMD GPU install tool as well as the package manager of your choice. Outside of the operating system and Linux kernel, this has been a touchy subject on a lot of the forums online, but you do want to make sure your GPU is supported. As the days goes on, I mean, I've definitely seen a growth in the number of GPUs that AMD is listing as supported. And again, what that means is that they're actually just adding them to their testing. What I have found is that even though some GPUs are not on that supported list, you can actually get things to work. Just your mileage may vary. I'll throw out a caveat here that I did not put in the slides, but I do want to mention is if you do have an integrated GPU, it will not be supported in ROCm. You'll actually have a pretty rough time. So you definitely want to make sure you have not just the correct GFX version, you want to have a discrete GPU that plugs into a PCIe slot or an Infinity Fabric if you're on an HPC system. Again, those supported GPUs you can find on the same spot where on the ROCm documentation, where basically it's underneath the system prerequisites section of their installation documentation. Now, once you've installed ROCm, of course, you can use ROCm info to get the GFX version, which is kind of like backwards, right? So you kind of want to know a priori what that ROCm version is to make sure your GPU is supported. You can find that information just by looking at the LSPCI output. If you're on a Linux operating system, it'll get you out the model name as well as the GFX architecture. But here, for example, once you do have ROCm installed, you can check your GPU version. ROCm info, even if your GPU is not supported for things like HIP or PyTorch, etc., you can use ROCm info to pull up that information as well. In this case, we're looking at an architecture, the GFX 1100. And now, like I said, some GPUs might not be supported. For example, the Radeon RX 6700 XT is not technically supported. It's not on that list that AMD says that they're testing. However, you can do some tricks to make it work with PyTorch and other applications. If you have this GPU, and even one of the ones we'll be talking about today on our systems, it's also not on that list. And the GFX version here is 1031. However, on that supported list of GPUs from AMD, there's a GFX 1030 is a supported architecture. Turns out that little patch version, which the 1031 here just means we're on the architecture is 10.3.1. Really all that matters is the minor version. So 10.3.0 is just fine. Those two GPUs with a 10.3.0 and 10.3.1 actually have the same microarchitecture. And there's an environment variable you can use to override what the whole system sees the GFX version, what it sees that GFX version is. So in this case, if you do have this particular GPU, or if you have any other GPU that has like a GFX 1030 or 1031 or 1032 or 1033, etc., you can set the HSA override GFX version variable to the most recent or the nearest minor version of that GFX architecture. So here we would set it to 10.3.0, and usually things work right out of the box. I say right out of the box, but after you set that variable, of course. The other thing to keep in mind is that if you're looking at the latest documentation, you might be disappointed to see that the GPU you have is not on that list. That doesn't mean it's not ever been supported. For example, at our shop, we have some MI50s as well as MI25s that we run. And actually, they do work just fine with older versions of ROCm. It's just they've dropped off the supported list. In some cases, I think our MI50 actually still runs with ROCm 6, but I don't know. I'm getting kind of hesitant to keep pushing the limits on how far that support will go, since it is on the deprecated list. But what you can do is look for older versions of ROCm and older versions of the AMD GPU installation and see if your system's on there. So if you do kind of lag behind, as a matter of like cost savings, you probably can do just fine working with an older version of ROCm. Okay, so I'm gonna pull up a few discussions that I've seen like crop up all over the place, particularly when folks are new to setting things up. And what we see a lot is folks who they get a system, they set up Ubuntu on it because it's nice and easy to get rolling, and then they have this problem where what happens is during the installation of the AMD GPU drivers, you see errors were encountered while processing AMD GPU DKMS. Usually there's additional output that says, hey, check the make.log for more information. There's another spot here now on the AMD forums where this has occurred. Another one, there's a compiler mismatch between the kernel and the AMD GPU DKMS driver build. All of this points to, in every single case, is folks just did not make sure that their Linux kernel was actually supported. So like, I mean, even right now, if you were to go download Ubuntu 22.04 from Ubuntu's site, the Linux kernel that comes with it is not the Linux hardware enablement stack, which would put the Linux kernel in this sort of unsupported state for ROCm specifically. Again, what you'll find if you check those make.logs that are reported from DPKG is that you'll see just complaints about some of the APIs from the Linux kernel not matching with what's coming in from the source code for AMD GPU DKMS. What I recommend everyone does is, again, before you even get started, make sure your Linux kernel's on that supported list for ROCm, if that's what you're doing. And right now, if you're on Ubuntu 22.04.6 on a fresh install, just install the Linux generic HWE, the hardware enablement kernels. Same thing goes for Ubuntu 20.0.4. Just the current versions they're at. There's just a different release cadence for Ubuntu than there is for ROCm, and sometimes things get out of sync. And in particular, on some of the older versions of Ubuntu, you do need to make sure you have the newest Linux kernel. So this is the way to do that. If you do this before installing the AMD GPU drivers, you should be in pretty good shape to avoid some of those problems and having to go down the Google hole of digging through forums where other people encountered the same issue. All right, so once you have the AMD GPU drivers, you have ROCm installed, then you can install PyTorch. So PyTorch, if you're not familiar, is a Python package based on the Torch machine learning library, which is a C++ code. In March 2021, PyTorch version 1.8 was made available for AMD GPUs alongside ROCm 4.0. In the background, Torch does use MIOpen, RockBLOS, and RCL to provide optimal performance on AMD GPUs. This is particularly why you need to have ROCm installed before you install PyTorch. At the moment, unless you're building PyTorch from source, you can install PyTorch with ROCm support via pip. You cannot do it via Conda at the moment. The beauty of the way that the developers of PyTorch implemented all this is if you have PyTorch code that runs on NVIDIA GPUs at the moment, you likely don't need to change anything. All you need to do is just change those package that's providing PyTorch in the background. Just point to one that uses the ROCm backends. You can still use the CUDA device type to run on a GPU. What I like to do in most of my installations, especially as I'm experimenting, is just to create a Conda environment. So here I'm on these few command lines, create a environment called PyTorch env with Python 3.9. Activate that environment, and the next line is where we're going to do the install with pip. If you want to get the latest, greatest version of PyTorch at the moment built against ROCm 6.0, you do need to use the nightly installation. So we're going to do pip install -- pre for the 3 torch packages. So torch, torch vision, torch audio. And then for the indexed URL, we're going to point to PyTorch's nightly builds for ROCm 6.0. If you did want to use the stable builds, you can actually use ROCm 5.7 just fine, even if you have ROCm 6 installed on your system. The only caveat there is if you're doing things with RockGDB, if you're doing debugging for some reason with RockGDB, or if you're doing profiling with RockProf, etc., you will very likely run into problems if your ROCm version is mismatched with the PyTorch, the ROCm version assumed for the PyTorch build. So at the moment, this is what we're running for our ROCm 6 installations on our systems using the nightly ROCm 6 build of PyTorch. That's how you do it. Now, coming up very soon when PyTorch 2.3 is released, which currently is estimated in July of 2024, you'll be able to get the PyTorch ROCm 6 build in a stable release just from the standard index for PyTorch's ROCm builds. If you're interested in like keeping track of that, where I find a lot of this information, like specifically for PyTorch, a lot of the other open source libraries, is they usually have a release markdown file in their GitHub repositories or their GitLab repositories, and you can find the release cadence there. I mean, for PyTorch, the link here is down at the bottom. If you want to check after you do the installation, you want to verify your code is working. You can just import Torch and just check that CUDA is available. That at least confirms that you have the correct installations there. If it is there, it'll return true. If that's available, you can also, for example, return the version of HIP or whatever that it's built against. That's just a quick validation just to make sure everything installed correctly. Now, aside from those little things, typically you want to do something a little bit more advanced, like allocate some memory on the GPU, run a simple kernel, etc. For us, of course, we are going to be running some benchmarks today. I did want to make a plug for this, just in case, there's folks out there that like using Docker containers instead of doing everything bare metal installation style. There are Docker images served by the ROCm team that have PyTorch and ROCm pre-installed. The only requirement is that you have the AMD GPU DKMS drivers installed on your system. You do need those AMD GPU drivers on the host system that you're running on, and then you should be good to go. Once you pull the ROCm PyTorch image, you can run it. You do need to mount the device files for the AMD GPUs, which are on Linux systems, going to be under dev KFD and dev DRI. So that is a pretty quick way to get started if you don't want to go through the hassle of installing all the ROCm stuff and PyTorch as well. You can just use the Docker container with the AMD GPU DKMS drivers on your host system. Okay, now let's talk about some benchmarks. So we have 2 systems we're going to be looking at that are hosted here at our shop in Hickory, North Carolina. On the left, we have our consumer system we've comically called Sega. We call it Sega because it's a gaming system. It's got gamer GPUs in it. On the CPU side, we have a 24-core Zen 4 architecture. It's the AMD Ryzen Threadripper 7960X. It's got multiple PCI V4 16-lane slots on it. In one slot, we have a Radeon RX 7600, which is definitely on the low end of cost for the GPU market. I think the last time I looked at these, they're somewhere around the ballpark of the 200 to 300 US for those. And then we have a more advanced card, the AMD Radeon Pro W7800, which is about an order of magnitude more expensive. So you're talking anywhere between $1,500 US and $2,000 US for those. but definitely compared to a high performance system, this is definitely a much more economical pricing. So we're going to look at how things run there, because we certainly have an interest in that. And then we have another system called Noether. It's definitely an HPC system. It's got two AMD EPYC 7313 CPUs. These are 16 core Zen 3 architecture on 2 sockets. We actually have, I should have corrected this, but there's actually 8 PCIe slots, 16 lanes, V4. Out of those 8, we've slotted in 4 MI210 Instinct GPUs, and this is definitely in more of the call for pricing category. So, right, we have 2 different completely scales of systems, and on the commodity system, we've got even there 2 different types of GPUs that hit different price points to take a look at. So hopefully you find that part useful. Of course, in the end, your benchmark is the only one that matters. For our RX 7600, which is actually not on that supported list because it is the GFX 1102 architecture, we will override that GFX version just using that HSA override GFX version, set it to 11.0.0, and then run our Python code. So in case you're wondering in practice how you would do that, you can either just export the variable somewhere else, or you can just put it on the same line and off you go. Things just work. Before we get onto our specific benchmark, one thing I always like to do when I set up a new system, and I periodically will check this, especially if I'm going through major upgrades of ROCm versions, etc., is we like to run micro benchmarks to exercise key components of the GPU. One of the micro benchmarks that we use is called Mixbench. This is an open source benchmark you can find on GitHub from the user Econdis. It's particularly meant to assess the global memory bandwidth and the compute performance. So it'll do floating point 16, FP32, and FP64 operations of varying arithmetic intensity. And as a function of the arithmetic intensity, it'll spit out the achieved flops per second and gigabytes per second. So you have both bandwidth and compute performance there. And then from this, what we're going to look at is just the maximum that's achieved. You know, we could look at a full roofline diagram if we wanted to, but just for the purpose of today, just want to show you what the maximums that we reach for various setups for bandwidth and flops. So here we're looking at a graph that shows on the x-axis the achieved bandwidth, the maximum achieved bandwidth for each architecture. So we have the MI210, our high performance card, up on top, coming in just shy of 1.5 terabytes per second. Then we have the W7800 at about half a terabyte per second, so that's 500 gigs per second. And then our less expensive gamer card, the RX 7600, is coming in about 281 gigs per second. So again, you know, as you spend more money, right, you get more performance out of this. This is what we should expect. But of course, at the end of the day, your total cost of ownership is up to you to figure out how that plays out for you. What we're looking at here is 3 different plots that show compute performance for float 16 on the left, float 32 in the middle, and float 64 on the right. And again, on the top row is MI210, middle is W7800, and the bottom is RX 7600. So going from the most expensive GPU to the least. We'll start with the float 16 diagram here. So we see the MI210 actually coming in at 41 teraflops. And in the middle, surprisingly, actually, our Radeon Pro card is actually winning out on the FP16 operations at 48.9. That's no surprise. The RDNA 3 architecture did come with some additional instruction sets in there to boost the performance of FP16. So you can actually see that bearing out quite well. So if you're doing a lot of stuff with half precision arithmetic, you might actually do quite well just getting a W7800 or any of the other Pro cards that are out there. But of course, if you're starting to do float 32 or float 64, this is where, you know, the HPC grade cards start to actually, come through in terms of performance. We already saw bandwidth wins out on the MI210 as should be expected. If I look at float 32, of course, we could see the sort of cost gets reflected into the performance there with the MI210 coming in around 34 teraflops. So this is not using the packed FMAs. If you're familiar with the CDNA2 architecture, there's an instruction called the packed FMA where you can do 2 FP32 fused multiply adds in a single clock cycle per compute core inside of each compute unit. These are not using those packed FMAs. So if I were using packed FMAs, in theory, we should be able to double that. Those packed FMAs are not available on the Radeon cards. Of course, Float 64, which is really what the MI210s were built for. They were built for scientific HPC applications. This is going to blow the other two out of the water entirely, particularly because Float 64 data types are not first-class citizens on Radeon cards. They have to use those FP32 operations to create a FP64 operation. So it just takes more clock cycles to do FP64 on a Radeon card compared to the CDNA. So that's what we're working with. Now, in terms of the PyTorch benchmarks we're running today, we're looking at two things: search time per iterate of our implicitly restarted Lanczos method and the energy consumption per iterate. To get the search time, we simply just use the built-in time package with Python, get a perf counter at the beginning, perf counter at the end, subtract the two, and that gives us a runtime. If I know the number of iterations I've done, I can divide by that to get me search time per iterate. We also look at energy consumption. So let me talk a little bit about how we do that. So on all of our systems, we set up a Prometheus node exporter and push those metrics out to Grafana, where we can do querying of all these metrics that are out there. All our resources are scheduled via Slurm, so we can use the exclusive metric to make sure our job is the only job running on those compute nodes. So if I can combine the database from Slurm, I can figure out start and end time for each of these jobs that we're going to run, and I can use that to query against the power consumption for each of those compute nodes and compute the area under the curve for our to get our total energy consumption for that job. If I know how much time was spent per iterate, I can take the average watts and multiply by the search time per iterate to get me an estimate of the energy consumption per iterate. So that's what we're using there for our energy consumption. We're actually going to look at a few different sizes, but the main one we'll start with here is a grid size. Sorry, it should be 500 by 500 grid. We're going to look for 500 eigenmodes, and we use a Krylov search space of 515. At double precision, this is just shy of a gigabyte of memory for those eigenvectors. With all the extra overhead stuff we need to do that search, I think we just peak out around 2 gigs of memory for doing this problem at FP64, which is quite economical in comparison to do a complete decomposition. We will look at FP32 and FP64 with the caveat that the implicitly restarted Lanczos method is quite sensitive to round-off errors, and we actually don't get great convergence with FP32. So in practice, we don't really care about FP32, but I figured since we can just do those compute patterns, you'd be interested in seeing that. All right, so what we're looking at here is the GPU runtime for our 3 different GPUs. So at the top is our RX 7600, middle is W7800, and the MI210 on the bottom. So longer here, the bigger the bar, the worse the performance is, the longer it takes per iterate to do this. On the top, we're about close to 2 seconds per iterate, and then down in the MI210 and W7800, we're actually quite competitive for this particular problem size. If I go to Float 32, of course, surprisingly, we actually see the W7800 pulling, coming ahead in terms of runtime. I'm not entirely sure what the reasons are for this at the moment, but this is definitely an area where we're going to be looking into hardware events profiling to figure out what's going on there. But it was quite encouraging to see that should we be able to improve convergence for FP32, W7800 would actually be quite an interesting choice for running these things, when we go into production with this code. This is the energy consumption here. Now, the actual values may not mean anything to you. Here we have them in units of joules per iterate, so how much energy was consumed per iteration of this run. Again, top is RX 7600, middle is W7800, and the bottom is MI210. The W7800 for both FP64 and FP32 came in at quite a smaller footprint for the energy consumption. This is for 2 reasons. One, the runtimes were comparable between W7800 and MI210. 2, the actual energy requirement for running this card full duty is much smaller than the MI210. Well, what this suggested to me was that perhaps the problem size was not big enough to fully exhaust all the resources on the MI210. There might be still more room to grow there. So we looked at varying the problem size. So down on the bottom here of this graph, along the y-axis, we're going from top to bottom. We're increasing the problem size. This line that says 250,000, this is number of degrees of freedom. This was our 500 by 500 problem that we've been looking at. Down below is cutting the grid size in half in each direction, so it cuts the problem size by a factor of 4. And then as we go up, we're going to bigger and bigger problems. The pink is our $200 to $300 card, the RX 7600. The green is the Radeon Pro with the W7800, and the top is our Instinct, the MI210. So on the x-axis here, we're looking at the runtime. So as we go out to these larger problems, particularly when I go from the 500 by 500 to 1000 by 1000 problem, you can see the MI210. This is where it really starts to shine. Now the W7800 is swamped over with work that it needs to be doing. The MI210 certainly has a lot more compute units available, so of course it's able to tackle larger problems. When we get to our 2000 by 2000 grid size problems, there's actually not enough memory on the W7800 to run that, but we can still fit that same problem on a single MI210 card. So it just goes to show you, just the different characteristics that you get based on the money you want to spend. So I hope this is actually quite informative for you guys in your choices of hardware that you want to run on. So just a few remarks before we close out for today. These results are preliminary, but they do suggest that the RDNA 3 architecture can be an economical choice for some of our problems, particularly these small to moderate sized problems in 2D. I think we can actually do quite a bit of useful science on without spending so much capital up front, which is quite appealing. And certainly we do appreciate the small amount of time we've had to do in code development, certainly developing in Python versus a compiled language using handwritten kernels and those kinds of things is quite time consuming. Doing all this in PyTorch was actually quite easy to do. And it's just nice to be able to do this on cheaper hardware. As I mentioned before, the IRLM is sensitive to round off errors. We do need some other work there to improve the stability of that method for FP32. So some of the results we shared there, I wouldn't say they're so meaningful. However, should we be able to get that improved, this would open up quite a few doors here for us. Generalizing our results, and this is where I really want to just kind of underscore a point here, is I presented just one example of a particular code that's meaningful to us. Generalizing this to your applications may not necessarily be appropriate because every application is different. They access memory different ways. They do different types of compute operations. And so I encourage folks to consider when they're looking at hardware, don't just look at how things run for other people's code. Think about how things might run for your code, and if you're able to get some kind of access to systems to test it out, take the opportunity to do that. The only benchmark that matters at the end of the day is yours. Here's just a quick plug for Fluid Numerics. You can find us online in a variety of places: Reddit, GitHub, YouTube, LinkedIn, etc. Of course, at our website. I'll leave a few minutes here for Q&A. So I did get one question here. Have you noticed any stability issues with RDNA 3 based cards? I'm asking because GoHots has been making noise on Twitter about its instability when using 7900 XTX. I'm not entirely sure what you mean by instability. Now, the only kinds of we've done tests where we've left benchmarks running for a couple days on end. And I got to say, I have not seen any kind of instability. I might have to get on Twitter and check out what GoHots is talking about. But in our experience with the 2 GPUs we've presented today, I have not seen any problems there. What is the reason torch text is not included in the pip install pre-torch command? I suppose it was an oversight. Most of the time, I just follow what's in the documentation. In our case, we down the line, we do have some other applications for our setup. We don't necessarily need torch text, but sure, yeah, you could add other packages there. I would just say it was more an oversight than anything. Apologies, I didn't mean to offend. Does the version of the host driver and Docker need to be the same? Is there a place where we can find a compatibility matrix? Yeah, the host driver and Docker, ideally you're the same. Yes, you probably don't want to make so like you can have AMD GPU DKMS one version on your host. What inside your container really matters is that the ROCm version is compatible. In my experience, So like on our systems, we don't do Docker containers. We have, we're actually running the AMD, the latest version of the AMD GPU driver, but we have versions of ROCm going back to ROCm 4 all the way up to ROCm 602. And there's no issues there. So I suspect that you could use varying versions of ROCm inside your Docker container, just as long as you have a good working version of AMD GPU DKMS on your host system. I don't think there is any kind of like discussion about this in the documentation, but it's certainly something that so if you go to AMD on AMD's GitHub page, it's github.com/ROCm. They do have a discussion section there. It's a great spot to drop questions. I know I'm not an AMD representative, but you can always check out stuff there. I respond to things a lot on that discussion forum, and so does a lot of the AMD team. So you can certainly probably get more information there. All right, next question. Someone says, I had the Mistral 7B instruction LLM model running using MLC LLM. I'm using ROCm, and I'm using my 6900 XT Radeon. The GPU is a problem? Question mark. I'm using the GPU, but is not supported to run over Linux with the version of ROCm that works with ML. I guess I'm not. If you want to follow up with a clarifying statement in the Q&A, I'm not entirely sure what the question is here. I don't know off the top of my head if the 6900 XT, it's probably not on the supported list, but what you ought to do is, I would say, check ROCm info, look at the GFX version. If it's a minor version, or if it's a, it's, I don't know what the GFX version is of that GPU, but if you find the nearest GFX version that is supported and just use that HSA override variable, that should work. My understanding is that that override variable it's not just specific to PyTorch. Like if you have a HIP code, I'm not entirely sure what Mistral 7B is written in, if that's HIP or OpenMP or whatever, however they're doing their offloading in the back end. You should be able to override that GFX version if it's not on the supported list. So I hope that helps. But yeah, feel free to drop a clarifying statement in the Q&A and I can get to that. Well, I appreciate the extra thanks that came through the Q&A. Thanks y'all for tuning in. Yeah, I think we're just about done for today. In the next coming months, we will be having future webinars on things that are related to artificial intelligence, machine learning, and of course, more HPC topics. So thanks for tuning in, guys. We'll see you real soon.